It's a term we hear and use every day, but its very essence can be a bit of an enigma. In the realm of physics, energy is often defined as the capacity to do work or the ability to cause change. It's this unseen force that enables us to move, think, and even exist. It's a fundamental concept that underpins every aspect of our universe, playing a critical role in everything from the smallest subatomic particles to the largest galaxies. But what's fascinating is that energy is not a one-size-fits-all concept. It manifests in a myriad of forms, each with its unique characteristics and applications. First, we have kinetic energy, which is the energy of motion. Anything that moves, be it a football soaring through the air, a car zooming down the highway, or a bird flapping its wings, possesses kinetic energy. Potential energy, on the other hand, is the stored energy an object has due to its position or state. A book perched on a shelf, a stretched rubber band, or water held behind a dam, each has potential energy waiting to be released. Then there's thermal energy, the energy associated with the random motion of particles. It's what makes a cup of coffee hot and a popsicle cold. Gravitational energy is another form, related to an object's position within a gravitational field. Think of an apple hanging from a tree, ready to fall. Sound energy, as the name suggests, is the energy associated with the vibrations of sound waves, while light energy refers to the energy carried by photons in light waves. And lastly, we have elastic energy, which is stored in objects that can be stretched or compressed, like a spring or a trampoline. So you see, energy isn't just a single entity. It's a dynamic, multifaceted phenomenon that takes on various forms, driving the processes and events that shape our universe. So in essence, energy is everywhere and in everything we do. Now here's an interesting fact. Energy cannot be created or destroyed. This is the essence of the law of conservation of energy, a fundamental rule in the realm of physics that governs our understanding of the universe. So what does this law really mean? Well, it's pretty straightforward. It tells us that the total quantity of energy in a closed system remains constant. Now, don't let the term closed system throw you off. It merely refers to a system that doesn't exchange any matter with its surroundings, and it's isolated from external influences. Picture a swing set in a park. When a swing is at the highest point of its arc, it holds potential energy. As it swoops down and picks up speed, that potential energy transforms into kinetic energy, the energy of motion. But as it swings back upwards, slowing down, that kinetic energy changes back into potential energy. This back and forth conversion continues as long as the swing is in motion. The fascinating part here is that the total energy, the sum of the potential and kinetic energy, remains the same at all times. It just changes forms. This is the law of conservation of energy in action. The energy isn't lost, it's merely transformed. This principle is as much a cornerstone in physics as the swing set is in the playground. It explains the workings of the universe, from the smallest particles to the most massive galaxies. It's why we can calculate how much fuel a rocket needs to reach the moon, or predict how much energy a wind turbine can generate. So the next time you see a car speed by or a bird take flight, remember that energy is being transformed, not lost. The gasoline in the car is converted into kinetic energy to push the car forward, and the bird's metabolic energy is transformed into kinetic energy for flight. And that's the beauty of the law of conservation of energy. It's an assurance that the energy in our universe isn't going anywhere. It's just playing hide and seek, changing forms, moving from one place to another, participating in an eternal dance of transformation. So while energy may transform, it never really disappears. But how do we measure energy? Well, just as we use grams to measure weight and seconds to measure time, we have specific units to measure energy. The standard unit of energy in the International System of Units, or SI, is the joule, named after the English physicist James Prescott Joule. Let's break it down a bit. 1 joule equals the amount of work done when a force of 1 Newton moves an object 1 meter. This might sound a bit technical, but think of it this way. If you were to lift an apple 1 meter off the ground, you would be using about 1 joule of energy. But of course, not all energy is about moving objects. Some of it is about heat. That's where the metric system comes in, with its unit of energy, the calorie. Now, this isn't the same calorie you see on food labels. That's actually a kilocalorie, or 1,000 calories. To avoid confusion, scientists often use the term small calorie for the metric unit and large calorie for the food unit. A small calorie is defined as the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So if you were to heat up a cup of coffee by 1 degree, you'd be using about 10,000 small calories of energy, give or take. Now you might be wondering why we have two different units for energy. The answer lies in the fact that energy can be transformed from one form to another, from kinetic energy or energy of motion to thermal energy or heat, for example. Different units help us understand these transformations better. So, whether we're talking about the power of a car engine, the energy it takes to lift an apple off the ground, or the heat from a burning match, it's all measured in units of energy. But what does energy mean to us in our everyday lives? Imagine a day without energy. No cars whizzing down the streets, no warm homes in winter, no reading your favorite book under the soft light of a lamp at night. Sounds unthinkable, right? That's because energy is an integral part of our day-to-day lives. Take your car, for instance. It's more than just a metal box on wheels. It's a marvel of energy conversion. When you step on the gas, chemical energy stored in the fuel is transformed into kinetic energy, propelling the car forward. And how about our homes? In the chilly winters and sweltering summers, we owe our comfort to energy. The natural gas or electricity that powers our heating and cooling systems is at its core energy that manipulates the temperature to our liking. Even at night, when the world outside quiets down, energy is hard at work. The soft glow of a lamp is nothing but electrical energy converted into light, allowing us to read, work, or simply navigate through our homes without bumping into furniture. But where does all this energy come from? The food we eat, for one, is a source of energy. Our bodies break down the nutrients in food, converting them into energy that powers everything from our heartbeats to our thoughts. The sun, that giant ball of fiery gas in the sky, is another major energy supplier. It showers the earth with solar energy, which we can harness to generate electricity. However, not all energy sources are created equal. Some, like fossil fuels, are non-renewable, meaning they'll eventually run out. Others, like solar and wind power, are renewable and more sustainable in the long run. We're constantly surrounded by and interacting with energy in various forms. It's in the warmth of a sunny day, the breeze that rustles the leaves, the food on our plates, and the light in our homes. It's what powers our world and drives our lives. Without energy, life as we know it would simply cease to exist. So we've covered a lot today, but what's the take-home message? We've taken a deep dive into the world of energy and physics. We started by unraveling the enigma of what energy actually is, the ability to do work or cause change. We then navigated through the law of conservation of energy, a fundamental principle stating energy can neither be created nor destroyed, merely transformed. We discussed various units of energy, like the joule and the calorie, and how they help us quantify this abstract concept. Finally, we explored the omnipresent role of energy in our everyday lives, whether it's powering our homes, fueling our bodies, or even enabling our very thoughts and emotions. Understanding energy and its conservation is not just for scientists or academics. It's fundamental to our existence and our future.